ज्यादा लोगों को पीछे से आंसर करना पड़ेगा. I need to, no, this is a screen. Yeah, it's okay. No, not required. I'll just see the slides there. It's pointed चलता है क्या इसमें? ठीक है. Continue on.
Hello. Yeah. Hello. Okay. Okay. So it's here. Yesterday we had this general body meeting, and she's the member of the general body, and she's the director of IIA, and I'm sure the most of people already know her, and she has also interacted with the senior student. And today she's here to give a talk. She has done research in various topics. She has more than 3 decades of research experience and published about 175 research publications in topics such as star cluster, stellar population, galaxies, ultraviolet astronomy, Magellanic Clouds, and many more. So she has vast experience, and she has recently got the Rashtriya Vigyan Puruskar, Vigyan Shri for 2024, and she has gone for the Vanita Ratna 2023 award from the government of Kerala in the field of education, science, and technology. Actually, she has received a lot of awards, and if you go to her profile, I mean, there are too many. I mean, otherwise it will take a long time to even read all of them. And she's a member of various academies also. And it is an opportunity for us to hear Professor Annapurni. And this talk was planned very, suddenly this morning we have discussed, and then she agreed to give a talk here, the student. So she will cover a lot of science she has been doing in the past 25 years, and you will see the glimpse of all those research works. So I'll request Professor Annapurni to present. Thank you.
Thanks, Yogesh. It's a pleasure to be here in Aries and giving a talk on what I've been working on and passionate about. I must also say that as Professor Ramsagar, who was the first director of Aries, I'm the first student of Ramsagar. So I'm happy to be here. And also I started working on star clusters. So it's a huge legacy in Aries on people working on star clusters. So I started my journey doing star clusters, but that was for a different purpose. But that gave me a broader platform to explore scientific questions on various other objects, so which I have diversified over the time scale. And in 2006, I was given the charge of doing calibration for Astrosat. That time, UVIT was getting made in IIA. I had no prior experience with UV, but I had prior experience with calibration, observations with telescope and calibration. So I was given that job. I had to find out what it meant and how to go about doing it. It was not an easy journey, but it was a lot of learning experience. And eventually, Astrosat was launched in 2015 in September, and it has completed 10 years in orbit. And eventually, I was a calibration scientist on Astrosat, which is this 2 yellow tubes. I hope I get your, yeah. So these 2 yellow tubes are the UVIT. And I continued as the calibration scientist. I will also tell you what it means to be a calibration scientist. Then I also did a lot of science with the instrument, because I got to know how to do the reductions, how to do the processing, etc. And early science was also not very easy, because understanding emission mechanisms in the ultraviolet is also a new area. So you need to understand why this object is emitting copious amount of flux in the ultraviolet. What triggers? What is the physical mechanism behind it? And these days, earlier, you can say that, okay, I'm detecting this is emitting copious amount of UVIT, UV emission. Is that enough? These days, not enough. You need to say, back it up with a theoretical model that, do you expect an emission? Which model gives you an emission? So what is the theoretical framework under which you can explain this emission? So which would mean that you have to also understand some amount of simulations and theoretical framework. Sometimes some gaps are there, you have to fill it up and then do it. So it was a long journey. So this part of the research in the ultraviolet is basically what I've done in the last 10 years or so. So I have put a little bit of Magellanic Clouds, which have started working when I was doing my PhD. And then I was so interested in looking at the clouds for various reasons, because these two are the nearby galaxies. They're interacting with each other. The stellar population there are very different from our galaxy. So it opens up so many questions. Why? How? So I was intrigued in various systems about it. But so every time I'll take an escape and look at Magellanic Clouds in some way and then come back. So I'll also talk about recent work which I have done on the Magellanic Clouds, and why is still research on Magellanic Clouds still relevant. So I'll just touch upon it. There are a lot of slides, but I'll just skim through some of them. So if you're welcome to stop me at any time and ask questions. So of course, quintessential, maybe this works. This one, right? Will I come out? No. Yeah, okay. Okay. Yeah, so quintessential, yeah, it's working. Quintessential is a description of IA itself, because I cannot escape this slide as a director of IIA. And I studied, I did my PhD in IIA when Ramsagar was there. So I became a faculty and then a director later. But IIA traces its origin to 1786, when an observatory was formed in Madras. And then it moved to its permanent structure in 1792 in Nungambakam. This is Nungambakam Observatory. So that functioned in Nungambakam till 1899. And 1899, they decided to move it to a more better observing place. And they did the survey of the southern hill stations, and then they moved it to Kodaikanal. And when Kodaikanal was formed, all those records which were there and things like that happening in 1792 in Nungambakam Observatory got transferred to Kodaikanal. Kodaikanal has been functional till from 1899 onwards. And last year we celebrated 125 years of operation of Kodaikanal Observatory. It is still functioning. I think you would have heard many things about Kodaikanal data from Deepankar, so I don't want to dwell into that. So it's still functional, and many activities, scientific activities are going on there. Then Kodaikanal Observatory became an autonomous body under the name Indian Institute of Astrophysics in 1971. So it's a long journey from there. And then before IA was formed, Kavalur Observatory was formed. And at that time, before moving to Kavalur Observatory, director of Kodaikanal Observatory, Venu Bapu, who's there, Professor Venu Bapu, was a director here in 1960s. And then he moved from here to Kodaikanal Observatory as a director. So there's a lot of connection between IA and ARIES in that direction. And around the same time, the proposal was moved to get a 1 meter class telescope to Kavalur. Kavalur was established, and also here, the call size 1 meter. And it was not going through because a lot of restrictions regarding foreign currency given to Germany, because it was coming from Carl Zeiss Jena. So then government said, okay, if you want to, we will somehow manage to make it. And somehow it happened, and then 2 telescopes came, identical. One was installed in, this is the Sampurnanand telescope, 1 meter, and 1 meter in Kavalur. Okay. Huh? You know, that was different. So these two came together from Vienna. Yeah, the Angapur Observatory was different. Sorry. Yeah. So in 1975, the headquarters moved to Bangalore because getting to Kodaikanal was getting difficult. So they moved to Bangalore, and then 2020, we celebrated the 50 years of IIA. So this is the whole history of IIA. And so as you can see, we have a headquarters in Bangalore, and then the Kodaikanal Observatory continues to be functional, which is derived from here. Then we established the Kavalur Observatory towards the end of 1960s. And early 1970s, Gauribidanur Observatory was formed to to do the radio studies of the sun. Now, actually, in Kodaikanal, before that, the antenna was set up. I think it's the Yeti antenna was set up here, and initial studies for the radio observations of the sun was carried out here. So the actual radio astronomy history in the country can be traced back to Kodaikanal. So many things, Kodaikanal Observatory, therefore, is you can see the seeds were sown there. And then we established both Hanle Observatory and CREST together in 2000. The reason being, Southern Peninsula gets both the southwest monsoon and northeast monsoon. So till November, from June to November, it is unusable. So if you want to find cloud-free nights throughout the year, you have to go past the cloud layer in the Himalayas. So there was an expedition set up in 1996 by Professor Kaushik, who was the director of IIA then, and found Hanle, and it was established that the telescope was it saw its first light in September 2000. So it's about 25 years. And at the same time, the condition was that not everybody can go to Hanle to take data. If you want to observe, many of you may be observing with HCT, right? You just need to go to Bangalore. So I mean, now the route conditions are better, people can go, but imagine 25 years ago, it's impossible to go. So people could go to CREST. The condition was that you should be remotely operable. So that's the initial condition. The design itself was made like that. So it was being remotely operated for the last 25 years also. That's why CREST came into picture. So these are the ground stations now. In the last 25 years, post that, we have been part of two major space programs. UVIT is one, which has completed 10 years. And then we established for that MGK Menon Space Science Laboratory in the CREST campus. And VLC is the next one, so which was launched recently. You would have heard more about VLC and Aditya L1 than me. So these two are the new ones. And Aries, IIA, and IUCA together are partners in the Mega Science project in JTMT. So Aries is also founding partner with it. And but the coordination center for this project is at IIA. So we also hold this, and the segment polishing facility for that is also sitting in CREST. So as part of contribution to India TMT, what is India doing for India TMT? We are contributing in terms of several hardware. So in-kind contribution. What is in-kind? Several parts being made here and shipped here, which means that you are making the investment in the country for developing the know-how in the country. And then you deliver that in-kind here. So what is it in-kind? So some mirrors and support systems and all that. Some heart of the telescope is being built here. Many of them are done in this industry, but then segment is done in IIA, and that is in the CREST facility. So and we are setting up a planetarium in Mysore. It's in the University of Mysore campus. There's almost construction is ready, and we'll be inaugurating in the next few months. And this will be added to IIA's one of the field stations from next year onwards. So this is the overall story of the institution called IIA. And a lot of things you can see that IIA and Aries have come done together and continuing to do moving forward. So coming to Astrosat, I hope most of you heard about Astrosat. Anybody who's not heard about Astrosat? Project students, you're welcome to say so. Then I'll be explaining. You'll have a bonus of getting to know about it. No, you still want to say that. Okay, then I'll skip this slide. So these are all the telescope in Astrosat, and I'm going to focus mainly on UVIT. Sorry. So just focus on this parameter. So what is the stable? The stable is that when you set off making an instrument or a telescope, you need to give them specifications. what does the user can expect when this telescope is ready? What will be its sensitivity? What will be its field of view? What will be the what are the filters used? What will be its resolution? What is the wavelength range? Right. So these are the specifications. Now this has to be made at the beginning of the project, and also when it is delivered, you have to tick off saying that yes, achieved this. That is when you say that it is actually performing to the specifications. If there is a change in the specifications, you have to record that also and say what is the impact of this change in the science output of this instrument. Okay, so this is an evolving thing you have to keep remember, or rather going back to this table and prove that yes, this is achieved. So you'll achieve at 2 stages. One, when the instrument is delivered in the ground, saying that yes, all these tests are done, and I can show that these are the measurements we have taken. So these are called calibrations. That's where I step in as a calibration scientist. And some of them can be carried out in the ground. Some of them you cannot, because your testing facility on the ground is not adequate. Ultraviolet particularly, there are many things which you cannot do. Some things only you can do in the ground, some things you can do in this in orbit. So something called in orbit calibration. So there, as a calibration scientist, I have to plan the entire calibration sequence. What are the objects I'll observe, why I should observe, how I should observe, how long I should observe, so that I get the enough data to give you all these numbers. Not only that, the calibration numbers, so that you can, when you take your data, you will be able to produce science-ready images, and you can do science with it, compare with models. So that is the job of the calibration scientist, and also to monitor its performance. Like I say, sensitivity is like this. Is it continuing to be sensitive similarly, or it's degrading? If it's degrading, somebody has to monitor, right? So I also do the monitoring part. So I also have to set up a system. How do I go back and calibrate, recalibrate, and how do I monitor? And when do I say you have to do the next calibration, right? Because this is concerning and I have to go back and check. And many times in space, sometimes the entire detector system will be switched off. Something happened, you switch on, then you'll say that, oh, if anything has changed, how do you know if anything has changed? You have to go back and check. So these quick checks have to be in place. So I'm not going into the details of it, but it's not like the ground telescope where you can just open it and put it back and see and do it. And the sequence of commanding is also required. So the process is a bit different. So what is UVIT? UVIT is a twin telescope. And I'll tell you why there's a twin telescope. Why can't you do an entire thing with one telescope? Just because there is a ultraviolet. If I'm shining a torch from here to that end, or even a laser, you can see the laser hitting that particular thing, right? It's optical, you can see. But in UV, will it hit the wall? Somebody is already sleeping. I'm just waking you up. Will it hit the wall? Anyone? Are we getting any UV radiation from outside space? Why? 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 Yeah, ozone, but what does it do? Absorb it. So is there anything in this room which can absorb ultraviolet? What absorbs ultraviolet? That's a basic question, right? Molecules can absorb ultraviolet. So absorption, so even if in the blue light, you have absorption, when you look at the extension, is very high. UV doesn't come in. So any high, shorter wavelength photon gets absorbed by any molecule around it. In the case of infrared, water is the most absorbing body. Here it is any molecule can absorb. So if you set up an instrument, you shine a light from here to test it, the light won't even reach the optics because it gets absorbed. So what do you have to do? You have to test everything in the vacuum tank. And the entire space has to be clean. You need to have molecular contamination to be as minimal as possible. And what happens if the light which is falling in? This is the primary mirror. So it falls on it, it goes to the secondary mirror and comes back, right? So all these reflections will reduce the flux of the ultraviolet, right? Light, right? So how will you make sure that if you make a far UV instrument, it is efficient? At least it is detectable. You can only have reflective surfaces. You can't have any transmission surfaces. Only filters is possible. That too, crystalline filters. So that is the condition in far UV. So you have to have only reflective surfaces. So in which case, you can only have one path length. If you have to split the wavelength into incoming beam into 2 set of wavelength, you have to have a beam splitter. Not intensity splitter, it's a wavelength splitter. But then one has to be reflective, the other has to be transmittive. So in Galax, for that matter, you may have heard of the Galax mission. There they have only one telescope. The far UV is reflecting, near UV is transmitting. But we want optical also. You can't have a 3-beam splitter. So NUV and optical are in one with a beam splitter here. Far UV is another one. That's the reason you have. So the learning bottom line for this is when you design a far UV instrument, it has to be as much as reflecting surfaces. You can't have transmitting surfaces. And you have to have special materials to make sure that there is efficiency is large. That's the understanding. Near UV is easy to deal with. So this is, so IIA had never built anything like that before. So we had to create a clean room and understand and create protocols. How do you make sure that the environment is safe? It takes about 8 years or something like that to deliver. All the 8 years, you have to run the facility and also make sure that it is contamination free. So you have to have coupons and then test it and make sure that if there's a contamination happens, how do you clean it up? All these protocols you have to follow up. So this is what is integrated. And so this is all the test things. And you can see this is a mass model. So it goes through a vibration system to make sure that this doesn't break when the rocket is launched. So all those we have to understand. This is a test facility inside the MGK Menon lab. And some are inside MGK Menon, like this is the vacuum tank within which the integration test is going on. These two are at ISITE, where the thermovac facility, where the cycles, it goes through heat and cold so that the instrument should still work. So all these things are done. This is a vibration table, vibration test. All these are to make sure that even if you launch it in a rocket and put it in the orbit, it still works. None of the parts get broken or not open, etc., etc. So you have to go to rigorous testing to make sure that this works. So this was finally launched in C30 on 28th September 2015. Yeah. So my activities was that the plan for all the things, including doors were opened on 30th November. So where will the UVIT look at when the doors are opened? I have to find the object and justify why it should look there. Is it safe? Will it get immediate image? Will tell you whether all the things are functional. So this is a heartbreaking situation where you're really keen to see whether actually you're getting an image or not. So it was a absolutely tense situation. Of course, it didn't get, because the first thing it opened, there was a bright object detection and the entire detector system got shut down. And everybody was staring at me. Why is this? You said this is safe to look at and get an image, and it didn't even, the BOD went off. So in next half an hour, we have to literally think and figure out what went wrong and how to, the next orbit when it comes, I have to get the image. So then change the parameters, made the commands, checked all the commands, uploaded the commands, so that the next orbit will get to know. So that was quite late. And then the data will get dumped only in the next orbit. So middle of the night only, we get to see whether it is actually working. So it was like a very stressful, tense situation, but eventually it worked. And so we had for performance, it's a wrong slide, so it's 10 years now, old slide, I mean. So performance verification was done up to March 2016. Again, all the observations, how to plan it, what all to be observed, why to observe, and what will I get out of it, all are my responsibility. And not only completing, delivering all the calibration products. So I had to, pipeline was not ready, I had to create my own pipeline to make sure that so you have to convert the count you get into magnitude. So, but you have to use standard stars and things like that. And so these are, this is how the international time, open time started. So these are which we look for. This is the tracking the sensitivity. I go back to the cluster NGC 188 because it's at the clear viewing zone. Anytime you can go to this cluster. And NGC 40 is for spectroscopy calibration. It's at 4 for primary calibration, and many things were observed. So this is how it started. And we continue observing the sensitivity, and it is actually, this is not the latest slide, but it continues to be within a few %. So it's really remarkable that the sensitivity has not changed. So the data is also public. You can see all NGC 188 data sitting here, all are public. So ISSDC, now it is moved to Pradhan, another system. So all the data is public. Even whatever I have proposed and everything is gone public now. So anybody can download and use the data. L1 and L2 data are available. Now, what do I study? I studied 3 different things. One is open cluster. All these are very familiar to you guys, right? I don't have to say what these are, but I can tell you why what is that I want to study in this. So in the open cluster, I would like to study which are the stars which are copiously emitting in ultraviolet. There are many cases where ultraviolet emission can be important, and why and in what circumstances is what I'm looking at. There are hot stars which are at the end of their lifetime, like white dwarfs, the subdwarfs, binary stars. So all these will be of interest. Globular clusters are stellar crash test labs, right? Where you can actually have stellar collisions. So what kind of zoo is it producing? And very important, this is an optical image of the globular cluster. It's very dense. You know, it's a extremely crowded area. But in ultraviolet, what happens is all these stars which are emitting copiously in the visual are all very dim, because they're all like, you know, cool stars, 5,000, less than 5,000. So they're not bright in UV at all. So all that you get to see is all brighter than 5,000 to 6,000. So even in many cases, you will even get to see the core. Core is even completely uncrowded. So that way, UVIT 1 with a reasonable resolution of 1.3 arcsecond, you can still observe it. I'll show that. And OB associations are OB stars, which are very bright and hot and bright stars. UVIT cannot see any of the hot stars because the detector is a different mechanism. I don't want to get into the details. If you want to understand that, I can explain. It's a photon counting mode. And if it's a too bright a star, then too many photons will come. And that is an electrons avalanche, and it can actually destroy the microchannel plate. So we have to restrict the number of electrons coming from here. So we cannot point it to any bright source. And even the bright source avoidance algorithm was written by me. And then later on, it was modified. So initially, when it was launch time, then we added more and more features to it later. But initially, I only did that. You have to check in all the filters. Then only the approval even come that you can, the clearance for observing the source. So why am I putting the OB associations? The OB associations are not in our galaxy, but external galaxies. The external galaxies, these systems become very faint, but these are observable. So these are what observing other external galaxies. Star forming regions actually stand out. So these are my science targets. And Chayan Mandal now did this PhD on galaxies, and these are this is the WLM, NUV, FUV combined image, and these are two other galaxies. So these are, what you all see is the far UV bright objects, and they're all OB associations. Now you have to see why the star formation is happening in this pattern, etc., star forming efficiency, etc., etc. Chan did his PhD. Now he is a faculty in SN Bose. After that, I could not continue my focus on galaxies because it required different types of, so many things. So I said, okay, let me focus on a few things. This is too much for me, and so I left. I don't directly work on galaxies, but on certain discussions on specific topics, I collaborate. But I'm not leading any of them now. And now, I have been mostly looking at star clusters, and these diagrams are most familiar to you guys, right? Color magnitude diagram, I don't think I have to introduce to you. Maybe first-year students are lost. So this is, when you look at a star, any object in the sky, you can measure its brightness. That's the first thing you get it. And you can measure its brightness in two filters, two parts of the wavelength, electromagnetic spectrum. And the ratio of the wavelength is actually, the flux in the wavelength is actually the temperature. So if you can get the ratio, which is basically in magnitude is a log scale, so the ratio becomes difference, right? Think about it. It's a very simple school thing. So the color, if you plot here, it's actually indicator of a temperature, color temperature, and then this is the magnitude. This is basically the magnitude of the scale, which I don't think I should introduce it here. So this is basically the color magnitude diagram, and for star cluster people, these are like the basic tool which we use, and you put all the open clusters on the same footing and at this particular distance is 10 parsec, absolute magnitude is that, then you can see that nicely falling on one sequence, which is basically the main sequence. Main sequence is nothing but stars when they burn their, fuse their hydrogen to helium. And that's a stable, most of the stars, that's a lifetime where they spend most of their lifetime there. And you can see something moving to the right. That is when the stars tend to exhaust their hydrogen in the core, and then the core collapses, the rest of the envelope starts expanding, and they move towards the red giant phase. So only evolution part you can see is onto the right side, cooler part. It doesn't go to the right side. It doesn't become hotter. That's one thing which you see. And the way in which it moves is depending upon the younger the cluster, you will have a broader main sequence. That means the mass of this is also equivalent to mass. The more massive stars are hotter and brighter, right? So they tend to live less. So they live less time. So move on to the basics. Now, what I was looking for is these stars here. So you can see this is the main sequence for a particular cluster, and these stars should evolve off to red giant veins. But you get to see these kind of stars which are left behind here. Now, what are these? Just like the physics principle I told you, it should move on to the right side. It shouldn't stay on the left side. Why? But initially people thought they're not members. Let us just ignore them. But later on we found that they are members indeed, and they're somehow managing to stay on the main sequence. Why? How? So they're called blue straggler stars. Blue straggling, so on the bluer side, and it is actually not following the path. So that's what it means. So my idea was to look at what is the formation mechanism of blue straggler stars. So so this is the color diagram. You see this in the case of globular cluster. You also see them here. And these are also brighter in UV because they are onto the hotter side. So UV will pick it up. So you will pick up these as along with other hotter stars as well. So you'll get a bunch of hot stars in the globular clusters. They'll have different, but you will never get the main sequence and things like that. So that is the difference here. And so this is to again wake you up. This is a nice cartoon made by Snehalata. She did a PhD with me. And you can see that this was found, the blue star is found, they're all yellow. And they said, how the heck you are blue? You should have become red by now. Then they said, no, you're not a member of us. You are actually from outside. But then we know that many of them are in the cluster only. So they're saying, how did you get extra fuel to stay on young? So then the possibility is that there are three possibilities which we find in the literature. One is a mass transfer in a binary where you actually have a compact companion, and this eats up the outer envelope, and you are left with a compact companion. This one, you actually have a collision and merge, it becomes a bigger star. And sometimes you can also have a triple system where the inner binary, the energy is taken by the tertiary companion outside, and the inner one merges, spiraling in. So it can be collision or spiraling in. So these are the three formation pathways. Now the question is, what is happening? Can you find out which is the mode which is happening in various places? People just say that this is possible, but what is actually happening? What is possible? And at the end, if you have a mass transfer, what is this dark companion going out here? What is is it just a white dwarf, or is it something else? What is the structure and what is its composition? These are the questions which we're trying to understand. And so the most important thing is, if there's a merger or a spiraling, and you will get only one star, there won't be any companion. But if there's any mass transfer, you will get a companion. So the point is that, can you detect this companion? If it's a recently formed binary, you should be able to detect this white dwarf, which is bright in ultraviolet. So the mass transfer pathway can be detected. And there are other things which I don't want to get in, like angular momentum, their rotation. There are many properties it changes, because mass transfer can change many properties. So how do you do this? The simple explanation is, you have two stars and A and B here, and one becomes a giant. And by the time it fills this Roche lobe in a Lagrangian, across a Lagrange point in the Roche lobe, it becomes a white dwarf, and this becomes a blue straggler. It can also happen within the main sequence, where the star the mass gains and it moves on to the main sequence itself, where the other one becomes a white dwarf. Both are assuming there to be white dwarf. Now, these are called blue stragglers, and these are called blue lurkers. This is a new terminology which has come in the last 5 years. It is indeed possible, but people had not detected it, that's all. And it's the same process. These both are post-mass transfer systems, period. These jargons are separate, but physically they are post-mass transfer systems. How do we detect it? So we have a long wavelength photometry, and in the ultraviolet, we are getting a UVIT and include Galax wherever available. So you can get a spectral energy distribution. VOSA helps you to do that. And then you can actually see the expected flux for this star is this high. It would mean that it is significantly high. This is the difference. And then you add one more component to it hot, you can get it. So this is the whole process. And this software is also developed by Vikrant, who is another student. This is a binary fitting module. It's freely available in GitHub. People use it, download it and use it. Huh? Yeah, blue lurker has to be on the main sequence. The star which you detect has to be on the main sequence. This is of the main sequence. So you have to have the turn off and then identify it above. So above the main sequence, they are called blue stragglers. And below the main sequence, on the main sequence, below the main tip of the main sequence, they're called blue lurkers. This is Kurus model for Stella. This is normal Stella model. This is normally we take Coaster model. You can also change because depending upon the range of temperature you get from VOSA. You can change the models also. So typically we use Kurus for the Stella, and VOSA allows you to choose most of it. But this is tailored for Kurus and what's the other one I said? Sorry. No, Kurus and Quester model. So sorry, just running out of memory. So this is how we do it. But there's also one more thing. In some cases, there will be some X-ray or some other detection is there. Then it means some other mechanism could be there. So what we're trying to say is that this is one possibility of excess flux being produced in UV. It's very difficult to produce excess flux in far UV. So how much can you plus, what mechanism can produce this excess flux in far UV? So now I'm claiming that it could be a stellar object with this temperature. Now for this energy to be there, I will also get a luminosity and radius. So you have to go back and put it in the color-matched diagram, say is it a viable product or not? And also look at X-ray. So first paper which came from this method is in 2016. This is the very first paper from UVIT. And this is one of the stars which we follow in NGC 188 has a binary. So for me, though the companion detection was the paper highlight, but for me, you can see UVIT and all the other IUE, everything fall in a one straight line after calibration. So it gives me good confidence that my calibration is fine and I can combine with all the other data to produce good science. So you can see that the cooler companion is actually dropping here and the hotter companion is going up. The combined flux is actually like this. So one single source is not possible to produce this much of flux. So this was like, so we continued with this and we have done a lot of open clusters and many open clusters are observed and so many PhDs were done and many students have worked on it. So this is the overall, you can go and, so this is a series called UOCS, UVIT Open Cluster Study. So far 16 publications have come under it. You can go and search for whichever cluster or things like that. So these are the things. Now this is one I would like to tell you is that this is an M67 and this particular star has actually 1007 has this much of extra flux. The spectrum shown here is the IUE spectrum. So it clearly says that even spectroscopically you are able to detect the ultraviolet excess. So modeling it gives you a, so this is a very tight binary. This has got a four-day period binary and the companion is actually a remnant of mass 0.2. Now, can there be a white dwarf with 0.2 mass? Not possible. Because right now, with the lowest mass star, which is evolving, which is as old as the universe, can produce only a white dwarf, which is of mass 0.4. If you want to make it a 0.2 white dwarf, then the universe has to be much older than that. The older, the still low mass stars have to evolve. You can only produce this low mass by stripping the matter from it. It has to be in a binary. So how do I verify it in a different way? I got this from SED and all that, but is it actually correct? Can I do an independent verification? So I use TESS and K2 data, and this star 1007 is a delta Scuti pulsator. You can see the delta Scuti pulsations here, which is normally, this is a post-Mass system. It is actually acquired mass, but it's still pulsating. So it's actually behaving like a normal star. You've added matter to it, but the matter has sunken in, and it is behaving like a normal delta Scuti, it's pulsating. But apart from the pulsation, you also see some frequencies in the lower frequencies. These are something picked up, but this is the common frequency here. This is nothing but a binary light curve. You can see the light curve is not symmetric. This asymmetric light curve, what does it mean? If you have an eclipsing binary, many of you are working on it, we'll have a symmetric light curves, right? It doesn't change, but here it is not symmetric. So this is very typical of a, can anyone say what it is? Ellipsoidal. Ellipsoidal means this particular component is oblate. So when the brightness is less, your cross section which is facing you is small. It's like a ball. It's like oblate, like a American football, right? So it is towards like you, then you have more area of cross-section. It is like you, then less area of cross-section. So the star is elongated. It is going and tidally bound. So it will go like this, right? So because of that, you get this kind of a variation. So it's distorted, but still pulsating. So we compared, it's a post-mass transfer system, how different it is from a delta Scuti star. Can you consider this blue star as a main sequence star? As to how they actually are burning the hydrogen in its core, and you can apply all the equations, but it seems to be okay. So this is what we did in this paper. So a highlight of this thing is that, in fact, we verified our method of SED fitting by an independent verification, which is giving the same values. So this now has been used by very things. But one more thing is, I said that mass transfer happens, right? So the mass is transferred. That's why blue straggler is the regenerated star. Now, can you see any chemistry difference on the surface of the star? Now, most of the studies in M67 said there's no chemistry difference, which would mean that you're not transferring any polluted matter. You're transferring the same matter on top of the main sequence star. Two main sequence star you add together, will there be any change? No chemistry difference, right? Like you mix the soil of this place from something 100 meters down, there won't be any change. But you mix the soil from something from south, you will definitely make a change, right? So so how do you make sure that when do you know this mass transfer happened? Do you know whether polluted matter can come in? So this is the first time we identified white dwarf with a S process element. So if you understand stellar evolution, the main sequence star, if it can go through evolution, then it goes to an RGB. Then it becomes a helium burning star, right? The core is helium is burning and it is converted into helium. Now, if it has more mass, it will go through an AGB. AGB time, there will be thermal pulses and the material will come in. The star has become very big. It's like quite a bit of a 250 times the radius. Now, at that time, you can actually transfer the mass from there to the other star. Now, when that mass is transferred, you have polluted matter. You should be able to see the material you expect on an AGB surface, which is called S process elements. So we detected S process elements, barium, europium, and lanthanum. So this is so this is the general spread of stars in M67. You can see this guy sitting here, and this is the star. And so this was the first detection of a barium blue straggler, but we also detected a white dwarf companion to it from UVIT data. So the first time you have many barium stars are known, but they have not seen the white dwarf. But when you see the white dwarf, you don't see a barium enhancement. So we don't know why both are not happening together, but this is the first case. Now we are finding more of them, but this is the first case we reported as saying that polluted companion with a white dwarf with S process enhancement. This also, Sharmila was a postdoc here, and she worked with Gajendra Pandey and me for her PhD. And this is one of the clusters which the 2818 is very special because the same name applies to the cluster and the Planetary Nebula. It has got a Planetary Nebula, and in UV you will see this Planetary Nebula very bright, and optically you don't see any of this nebulosity. So this one and this is only one or two open clusters where you have nearby Planetary Nebula. You expect Planetary Nebula to be plenty in open clusters. We normally don't see it all. Only a couple of them are known, and this is one. And in this study, we proved that this central star, so UV, if you see in the UV, you will see the central star. In optical, you don't see the central star. So because of this UV luminosity and correcting for all this flux corrections and all that, we can get the total luminosity of the central star, which puts it here. So it helped us to say that, okay, a star evolves from here, can actually be part of it. So this is, in fact, most likely to be a member of this cluster. So that was the takeaway point from the study. And there are many studies which now we find that the star is actually oblate and with this a companion. So these will show ellipsoidal variation. So many test data can be used, but tests, and this is mostly K2 because TESS has got a larger footprint. So there will be contamination from nearby sources in a cluster, so that one has to be very careful. So in the previous study, we combined both TESS and K2 and used only TESS that part where K2 is also seen. So one has to be very careful with that. So in that study, we used Dominic because Dominic was an expert in TESS and delta Scuti also. So what do we see at the end of the day? So we have another figure, but you can see that the stars are sitting here. As I said, are we getting white dwarfs with the companions? We are not getting white dwarfs with companions. We are getting, these are something called low mass white dwarfs or extremely low mass white dwarfs. And we have some of them, they are SDBs and SDAs. So you can see these lines, these are the white dwarf sequence. So normal stellar evolution takes you on this path. Then you have, like in the previous slide, right? I showed you here. So this is the stellar evolution for a particular age. Yeah. And then it comes like this. In between, whatever you see, what are these? They cannot be produced by single star evolution. These are all produced by binary evolution. Now, we also found that the binary evolution is not producing white dwarf straight away. In many cases, I think I'm going in the opposite direction. It is in fact producing a plethora of stuff. And depending upon what kind of a mass transfer is happening, they are falling in various places. It can be SDAs, SDBs, ELMs, white dwarfs, etc. Now, the most important question we need to understand is why are this happening and what conditions, what is happening, right? Because what can you expect as an end product if in what scenario? If I have a scenario, what can it produce? Can I model it? Right? So that is the question I'm trying to look at in the future. Because I have so many samples. I know their ages because they're all in open clusters. I know their properties. But I need to understand if I have an outcome of these two, where did they start with? What did they went through? What did they go through to arrive at this point? So can we predict binary evolution if I see the binary? Not done so far. It's not easy to do, but then it's a good attempt to do. So I would like to pursue that. Yeah. The same thing. Yeah. Yeah. This is the updated one. Yeah. Sorry. Yeah. Yeah. Here also, this is a 1.3 solar mass. This is 0.5 solar mass. So you expect most of them to be here. Some are here, but not all. They go to low mass and then they become like this. And if you look at the field ELM, there's a lot of extremely low mass white dwarfs found in the field. And you plot them, they're all here. They fall beautifully on top. And there are SDB, which are known in the field, subdwarf. Subdwarf is hotter than the base sequence stars. We don't know why they're hotter. They should have shed their outer layer. Otherwise, they can't be compact. They're hotter. You can say this, they're less luminous also because they moved on the right side. So sorry, left side. So they moved here. So these are field SDBs. You can see the SDB and SBO. So this is what we are getting from the cluster companions. So these are all binary mass products. Whatever you're seeing in the arrow here are coming from so many clusters. So this is a consolidated outcome from so many clusters. Yeah, so you have to, the SED is there, right? Yes. Yes, it gives you the area under the curve is the flux, total flux, right? So the curve which is fitted is a spectrum for a particular temperature. And you know the distance to the cluster. You can give the distance to the cluster, you know the reddening to the cluster. So you give that reddening and you can actually put the flux. And then you fit two spectra to make the... Yeah. So excess flux is like if I can draw on the board or I can go back. Yeah. Yeah. We have this flux here and lambda. So you will have data points like something like this. You have data points. Then you have to, let's say you have this as UV and all that. So you have a spectrum which is going like this, let's say. Okay. Typically, you have a data point here, data point here. You have to get the observed flux and the model flux. Right? Yeah, VOSA you have. And you have to find this fit up to here and find what is the excess. Now you will get the difference will tell you this like this, right? Now you have to fit this. So you have to bring in another component and fit it like this. So it will be something like, so the overall luminosity is much less because area under the curve is much less, but it is hot. The contribution is much higher in the shorter wavelength than in the lower wavelength. So you will get the area under the curve of this and area under the curve of this. That'll give the total luminosity. So you will get the luminosity. So for each, you will get L, R, and T. So you can also verify if this is equal to white dwarf radius or a ELM radius or something like that, subdwarf radius. All three you will get.
Yeah, but you will see at this.
Yeah, so we model only beyond. No, you won't see excess emission. You will get a stellar spectrum with emission with fits one temperature. Here you can't fit the entire spectrum with one temperature. That's all I'm saying. In the pre-main sequence stars, this is not the case. You may get this. You may get this also, because this is the magnetospheric emission. In T-Tauri stars, there is this. I'm not covering that publication. We have studied T-Tauri from UVIT also. So you have to model this with magnetospheric, and this is the disk contribution, infrared. Both you have to manage. In this case, it doesn't come. It's okay, yeah. Yeah, so this is the summary of, I think we have one more added recently, but that's not here in this. So, yes. Yes. Yeah, so there are studies which classify binaries into different period orbits, like shorter than 1 day, 1 to 10, 1 to 100, 100 to 1,000, and beyond 1,000. So beyond 1,000 is very long. The binaries don't know that they exist. The other star is existing, and they evolve independently. 100 to 1,000 is when we see that space is more than enough for the one star to become AGB, and mass transfer happens. 100 to 10, you can have case B or case B mostly when it becomes subgiant. It can fill the entire Roche lobe. It can either go to a common angular phase, or it can transfer the mass and become a low mass white dwarf. The shorter ones, it's very difficult. You could actually have a common angular phase and entire thing can be thrown. This is how the story goes like. But then once the mass transfer starts, the viscosity and everything changes. Circular is the period. Sometimes they come together. It's not, energy conserved system. Then it'll be difficult for you to actually model and say exactly how this is going. But you have to have certain constraints. If these are assumed, this is how it'll progress. Yeah. So in a cluster, one more problem is there. They're moving in a central potential well of the cluster. So they have random orbits. They can collide. So that can also change the orbit. In your case, in the field, then I think they're isolated systems. So their periods are unlikely to change, and you can model them in the field. The field, the problem is you don't know their age. So here you know their age. So within what time scale this is going to happen, right? Time scale is important. It takes 1 giga-year for it to happen, or 500 million years to happen. Yeah. So moving on. So I just want to touch on globular clusters. I think a lot of work is done by Ramakant and his students in this thing. You would have listened to their talk. So I'll just quickly go through it. So globular cluster, we did something called a legacy survey. But before that, we had observed a lot of globular clusters, which was mostly part of Snehalata's thesis, and some was also used by Gaurav. And so we processed most of it in the, these are the many things observed, and we put 11 of them together in the first legacy survey. And these are the people used it. You can see familiar names here. And Deepti also, sorry, Snehalata, Sharmila, and Deepti all used this. And this is you can compare this is the optical, and that is the UV. You can see the difference. So all the main sequence stars get suppressed, so crowding is much less. In many cases, the first few arc seconds may get crowded, but the rest of it is quiet. And centrally, because the blue stragglers are massive, they're all towards the center. So you will get to detect more of blue stragglers in the inner regions. Same with horizontal branch stars, also more there. And so there are sort of a lot of exotic populations which you can detect from it. A lot of data is public. Many data of globular clusters not used. Anybody is welcome to use so. So we had done the legacy survey. Some we have published, but some I didn't get time to do it. So some are not published. So what did we do? We brought all the 11 clusters together and make a consolidated diagram, like the one I showed you for the clusters, right? So this is how maybe you are familiar with the globular cluster calorimetric diagram I showed in the first. So how does it work is that you have in optical, you have a thing like this is a RGB, and the horizontal branch is like this. This is nothing but helium core burning stars. RGB, they start the helium burning from here and they sit here. But when this is a constant luminosity because the mass of the helium core is the same as 0.45. So the luminosity should be the same. Now what determines its temperature, the luminosity is the same, but temperature will depend on this is the core, how much is the envelope. If you have a large envelope, it's sitting here, but you have less and less envelope, it will go here. Now what decides the envelope? Mass of the star. Second, also metallicity. If the envelope is small, but then you have more metal absorbing metals, then the flux in the shorter wavelength is not coming out. It's getting absorbed by the metals. So you still be here. So this is called red horizontal branch. This is be there for metal-rich globular clusters and younger clusters. But as they become older, it become like this. This is the optical. Typically, this is B minus V, let's say. But if you look at the UV, the horizontal branch itself is slanting because it's more temperature sensitive and bolometric correction is like that. So this yellow is the horizontal branch, and you expect the horizontal branch to go extending like the slope, but you can see the flattening there. Flattening is happening at a place where there's something called diffusion is happening. So you have flux coming up, and then you have the metal or the heavier nuclei sitting close to the core. They get kicked up because of the photons. So you have artificial enrichment on the surface, which will lead absorption in the ultraviolet, flattening it. So this revealed exactly at what temperature this effect is starting. So diffusion is starting at that temperature across the cluster. So far UV can be used at this. That is one. Second, the stars which you're seeing above it are the post-HB stars. Now, initially when we created these, the models are not fitting. We had to talk to BEST people and say, you have to introduce this much of diffusion to actually match our models. Then they changed the diffusion. Now the models are matching. So that is one. And this is the white dwarf sequence. And this is the blue stragglers. This is the current this thing. The previous one from Galaxy was this. They didn't have membership. Of course, we have membership. So you can see how clean diagram we are able to get. So yeah, these are the two from Shavanita, and this is the diagrams from UVIT. So a lot of work can be done, but every work demands more understanding. So these are the RLA stars, eclipsing binaries and RLA stars sitting here. And studying RLA stars in the UV is also not done. Data is available. So this is Arvind's paper, which is 362 has been a hot target. 360 was part of that cluster also, but then we pursued it. This is the binary sequence of blue stragglers. You can see the blue and the red, which would mean that the blue is likely to be collision product and the red is supposed to be the mass transfer product. But all that we're saying is that we don't detect a companion. That does not mean it's not a binary. It could be the white dwarf is cool, but we happen to see this, but it's interesting. And their counterparts are low mass white dwarfs. Here also blue lurkers and globular clusters, the first blue lurker study in globular cluster. So this 362 has blue lurkers. And this is an interesting study. Initially, we were a little hesitant, but then we clearly detected the high. You can see the amount of excess you are getting. This is quite a bit of excess. We expect this to go down. Here also, there's too much of excess. So this is combined with HST data, so there's no problem with resolution. It's not like misidentified or anything. Again, another one is I showed the the white dwarfs. So these have massive white dwarfs, which is also known because this can be the formation pathway for magnetars from globular clusters. So recent study shows that there could be magnetars in globular clusters. Nobody knows how. So this is a core collapse cluster. The core collapse may produce binaries and it could form. So this is the result from this paper. I'm just running through. If you have any doubts, you can stop me and ask. So this is the thing. And we also had 1261. This is a cluster with a lot of RLA stars. All these RLA stars are sitting here. You can see we have so many detections across filters. And this time series photometry is also done for this. I mean, we have observed it. If anybody interested, 1261 data, plenty is available. Observed, but nobody has reduced it. It's a bit of a laborious work, but up for grabs. No, multiple orbits are done. So you'll have to reduce each orbit and then combine it. And there is actually Prajwal, who is at UVIT POC. He has created one, forgot the name of that algorithm. You have to extract photons and then do the photon counting. And then you can actually put it into a code. This code, it will give you a variability. So that is also there. The only thing is somebody has to do it and then put it into a code and see variability. Sometimes the code may not work. You'll have to find different ways of plotting it, because hourly array, you know what the period like, less than a day or typically kind of a day. So UVIT orbits are 30-minute, and it takes another 1 hour to go back to it. So there'll be gaps. There'll be, it's not a easy task to do, but only thing is in UV, for UV, the amplitude of variation in ultraviolet UV, sorry, RL array is about 3 magnitude. So you will catch it. Yeah, sorry. No, right now we have science study data. You have to download it and you run the photometry first. So this is not photometry, is not done. So source catalog is not available. It's difficult because you have to different algorithms for see many things. You can even see in this picture itself, there are galaxies present. So we'll have to make sure that the galaxy has to be removed and all that, because background galaxies are quite bright in UV. So, I mean, you can still do a source catalog and produce it. There was a recent release of the pipeline, which had some modifications. Now, the aim is that now that we are processing all the data, all the freely available data can be run through this pipeline and make into a source code, point source catalog. So that we are planning to do, yeah. So this is another case where we found mass transfer binary in NGC 546. This is one of the earlier publications. Gaurav's paper, which we found an EHB star to have a blue straggler companion. So each cluster throws out a lot of interesting objects to do. This is Deepti's work on NGC 2808. And this, sorry. Yeah, so these are, so people generally say that once it goes onto the horizontal branch, it goes through the AGB phase and it goes like this. That was their thinking. But actually, when you saw even in the color magnitude diagram I showed, many of them were sitting on top. We are not finding anything here. People expected to find here. Did you find anything here? No, we didn't find. We are finding something here. Now, what are these? So these are post-HB stars. These are called HB Mank stars. So as I mentioned in the outer layer, what decides a star to go through AGB is you have to have enough envelope to expand. This collapses. The core is collapsing, carbon oxygen core is collapsing. It has to expand. And enough mass has to be there in the envelope to expand to become an AGB, thermally pulsing LGB, etc. And then further it cannot go, but it will come down to a white dwarf. Now, if the envelope is so thin, it cannot expand. It can only go to some luminosity, and it will come down to a white dwarf stage. So that is what we are finding here. So these are called AGB Mank stars. So many of them are not here or here, they're here. So most of them are not able to go through AGB phase. So the main understanding is that if you want to say you have an elliptical galaxy, a nucleus of the elliptical galaxy is UV bright. What is contributing to the ultraviolet? Is it star formation? Is it new OB stars or old stars? Okay, can old stars contribute so much of UV? How can you find out? You have to have some number, right? It is possible or not. People used to tick this luminosity and say, I scale it up. So many cluster will have 10 such stars. I scale it up this into 10 and I get this luminosity. Yes, possible. And we're finding that hardly anything is here. It's all sitting here, 1 order less or 2 orders less. So they cannot produce luminous stars. So NGC 2808, in fact, you can see how dense it is. One of the dense globular clusters. Even that is not able to produce such bright stars. Even if you look at poorer clusters, you may see 1 or 2. You expected all of them to be sitting here. It's not happening. So this gives quite a bit of a limit on how much UV luminosity a old globular cluster can produce. To see such thing in elliptical light. So that was the implication, but I didn't want to go into the details. Everything has a story to say itself. This is the same thing. We found only one in this cluster, 2298. Most of them are in the red horizontal branch, some are in the blue, and they're not going here. They're all coming here. So the brightness is not that high. You're not getting at 10⁴ luminosity. They're all at 2, less than 3. So that affects the total luminosity, UV luminosity you can expect. So this is the omega sun. This is another crazy cluster where multiple populations are there. So we had to actually model it. So we modeled with multiple population, and then you can see different types of population here color coded. And what we observe is that this is very faint. Never seen in other clusters. So we find that they are low mass. So it is similar to M13. So we see that is happening in M13. Most likely the mass is lost. Envelope is quite small, and the entire luminosity further comes down. I showed that this is flattening, right? This is because of elemental absorption. Here you have much less material, it still goes down. And that's to do with mass loss and helium abundance. So you have to model together helium abundance and mass loss to bring it. And that produces low mass white dwarfs. M13 is known to have, there's a Nature paper which said these white dwarfs are low mass. That is produced by excess emission, excess mass loss, the core doesn't grow. So new physics and new models that have to be incorporated, new schemes have to be incorporated in this. So Magellanic Clouds, we've done some studies. So these are done by Sipra's work. So maybe I should, yeah, okay. So small Magellanic Cloud is a galaxy which is part of, maybe I should come back here, sorry. I just put it, so this is the Magellanic Clouds. The small and the large, these are two neighbors, and there's a large cloud and the small cloud. In the sky, it is separate. You can see from the southern hemisphere, you can't see from the northern hemisphere because the deck is -63. Now, if you put the gas, they're all together. There's a bridge connecting the two. There are all sorts of things happening. So you now know that none of the galaxies have gone through without interaction. So if you want to study what happens to a galaxy when it interacts and goes around, this is in your backyard. This is about 50 kiloparsec and 60 kiloparsec, not very far. So you should be able to understand what happens, how the gas gets truncated, what happens in an interaction, kinematically, stellar population, everything. And so this is distribution of star clusters in this. You can see this matter coming out. So this is stripped. So SMC is more stripped than LMC. LMC, you can see this is the bar of the LMC. So many things. So this is the LMC and SMC. The SMC is more gas rich and a lot of star formation has happened. So now I'm going back to the previous slide. So this is Sipra's work where we took, you can see each footprint is UVIT image. So so many fields are covered in central part and the northern part, shell part, and the inner wing. And we combine all the data, reduced, calibrated everything, and then it is available as a catalog now. These are massive stars, total 93,000 stars. And so these are useful for things. So mainly we have, I'm not covering most of it, these are 13,000 far UV stars. We are dividing into double binaries. So we have this in 8 filters. We are trying to see in massive, many of them are more massive than 5 solar mass, 5 to 8 solar mass. Now in that category, how many are become binaries? And what are the products? So this is being done, and many are algol binaries. We have 18 stripped binary systems. So you know the Wolf-Rayet stars and things like that, right? There the outer shell get stripped off. So many things are, so we are able to find stripped systems. So in the UVIT data, and we are able to find their properties as well. I'm not going to the details. This is there in some of the upcoming papers and published papers. LMC, such data is not available. Some data is available, but not all are there. It's a very large field to cover, and many fields are quite bright. So this is done in using 163 M. So it's a moderate filter, and it's not one of the efficient filters. So we somehow managed to get data without LMC. No, they're too bright, and BOD will happen. So you can see in this, you can see a gap in the center. That is because too much of brightness. We could not clear it. So only this much of observations could be done. Yeah, so this is there, the results are there in these papers, and a lot of work needs to be done on what they are, what their properties are, etc. So this is Sipra's work. And so Dhanush's work was to look at the star clusters and identify them and find out the star formation history across. Now, why now? People have done it before, but this is from Gaia. You can see it spans a large area in the sky. Unless and until you get a survey data, you can't cover the entire thing. Your telescope will not be able to cover entire thing. So this is from Gaia, and we can actually do the filtering by automatic process. So we actually have an automatic process, and I take isolated clusters and overlapping clusters, and these are the overlapping clusters. Now, if you make a CMD of this, we'll have stars from both the clusters. It's not able to separate out. So we considered only isolated clusters. And then like that, we analyze. So these are the isolated clusters shown here. So this is the method. And so eventually we have these many stars, and you can see the star formation history both. So both went through some episode in these times, and then the star formation kind of died. You can see that the older stars, which are starting from 1 giga-year to 3 giga-year, they're all spread out in a much larger area. Then the entire galaxy has shrunk. The recent clusters are actually blue and green. They are in inner part. That means that the galaxy lost gas in the outer regions. There's no star formation. You can see that's not happening in SMC. The younger clusters are being stripped out because the gas is being stripped out of SMC because of tidal interaction. So these are the shrinkage of cluster formation. So you can see that the entire cluster region of formation is actually shrunk. And you can see exactly when the bar is visible. Bar tends to start getting visible by this age. And by this age, you can clearly see 100 million years, you can clearly see the bar enhancement in clusters. So how bar as such doesn't exist now. So what is a bar in LMC has been a question which I've been following up for the last 20 years. Still, in stellar, you can see, in gas, you can't see. So that is a kinematically difference. You'll see that. And SMC, you see the central star formation has been always active. But the galaxy is a bigger galaxy. So now you can also do a kinematic modeling. You have, what is kinematic modeling? You have now proper motion, right? In a galaxy, how do the stars move? With respect to the center, they go around. If you actually look at a galaxy, what is the galaxy doing? Galaxy is moving, and also the stars are going around the center with respect to the center. So you will see both like this here, right? This is a nearby field and the clusters. You will get this. Now, what the heck are you going to do with this? You have to get the overall motion, systemic motion subtracted. Then you will get the intrinsic motion. Now, this is the motion you see. This is not the actual motion because this galaxy has got an inclination, and it is with respect to an axis, it is inclined. So you have to model it. So you do thorough modeling, you will get the rotation curve. And also you can tell how much is the dispersion in velocity across the cluster, across the galaxy. Is the galaxy hot? Is this clusters hot? That means it's got some chaotic phenomenon happen. It's not really. You can actually see the velocity dispersion is 20 kilometers, which is typical to our disk of the galaxy itself. It's like typically 20 kilometers. You look at our halo, which is about 100 kilometers. Thick disk will be about 30 to 40. So this tells you that it's not actually hot, but it varies in different population. So this is the kinematic modeling of the LMC, and it'll give you all the parameters. And we also find that the younger have a steeper rotation curve compared to the older clusters. This is the result from the clusters because you have age dating for the clusters. You can't do with the other population. But with RCN, field you can, field is a generic, but RC means between 1 to 9 giga-year. So this is the perspective of the disk. And I don't want to get into, because it's actually the inclination, and it's actually varying like this. So there are warps in this galaxy, and inclination also changes from inside to the outside. So it's disturbed. But it's not disturbed to the extent that overall things are not changing, but then there's disturbance within. So this also, I think there is a video for this changing. You can see the inclination changes and the warp building up, right? It's like this. Yeah, so the galaxy is complex and it has gone through perturbations. That's what it means. So we also did where exactly the implication, where interaction, where do we see? We see the interaction peaking at about 100 million years. You can see this peak coming here. This one. This is about 100 million, 100 to 150 million years. So there have been some counter-rotating clusters. So there's something interesting happening over there. And we also see that the models, can you do the modeling? You also see that it must have gone through an interaction. LMC and SMC, now people think that they collided 150 million years ago. Now people are looking for where did the collision happen? How did they pass through? What are the implications, etc. People have been looking at. It's not easy to find. It's horribly difficult to find. So we actually have star formation rate is, we know that there's an enhancement, but kinematically, how can you find? There must be some disturbance, right? So this you can see is once you have the model, you can subtract the galaxy component. After subtracting, you should find the hot component which is disturbed. It is not coming here actually. You can see nice bar. Bar obviously is not a circular motion. The bar imprint is there. You don't see much of a kinematic shuffling. So it's still a puzzling thing. Yes, yes. No, before that, it was like about a few giga years ago. Yeah, 2 giga years ago. Not too many. 60 million years? No. About 45 million years, there has been a close passage through the galaxy. So there has been star formation also. So SMC has been done. You can see again the same pattern. SMC is difficult because the galaxy as such is small now. But if you look at red clump star distribution, it's very big. It's actually a big galaxy. But the young stars, you see the small galaxy, and you can model it. And we see that only rotation is possible with the young stars. Older, it is a spheroidal galaxy. And you can also play a video here, which tells you how the galaxy in different populations. You can see it nicely processing. This is the old stars, and the new stars is actually changing its inclination. Because of that, the large depth is seen. So this is the actual, you see the galaxy through this. You see this stretch? So this is the 3D view of the galaxy. Okay. Yeah, so this is how will LMC and SMC put together, we'll see. Right? You have the perspective of LMC, and so this is the overall structure. You can see that, and pause it here. You can see that the older population is here. You can see the stretched towards here, to the galaxy. So this is basically the gravitational interaction and the tidal interaction. We have some connecting features and things like that, old bridge and offset, etc. And we see some tidal implications and some kinematic features that are also identified. And we see that there are some features which are moving slower and some features which are moving faster. So the galaxy is actually quite chaotic. Kinematically also it's chaotic, not as much as, but older population is fairly decent. If you can see this, there's not much of a change, but you can see getting chaotic in the younger population. So this is some of the results from there. There's also some work by Cauchy, which I have part of it, called jellyfish galaxies. They're very interesting because they're falling into a galaxy group and their gas is stripped, and this gas forms stars. And these stars are not too much, so you can not detect them very many in the optical, but UV picks up very well. So this is a jellyfish galaxy, one first we detected, and Cauchy was leading this part. So this is the galaxy stripped, and star formation is happening here. So the central region also has got an AGN, its upper star formation is also there. So he has done a lot of work and recently also detected in various surveys. Yeah, so I'll stop here. This is slides for insist, I'll stop here. And sorry for putting some all sorts of random things.
So you can see a lot of work. I mean, he has done all this work last 25 years or so. And each slide contains, substances for over 1 year.
Yeah,
And you can
most
see
of them
that.
are in the last 10 years. I don't think I've found anything.
Yeah, even the Basnic.
No, that's also 10 years.
Okay, 10
Maybe
years
some
stuff or missing.
thing in
Okay.
10, that's
Yeah.
between after 2020.
Okay, okay.
Yes, all
Stand
of
for-
them are between last 10 years. Yeah,
Yeah.
I haven't gone beyond that.
So now, if you have any question, you can please ask.
Yes, yes, a lot of agents are observed. Agents are observed along with the S60 also, because many of them are observed with, Astrosat is basically like a multi-wavelength instrument, right? So you need to have, all that I've shown is that I couldn't combine anything from LAX-PC or X60. Main reason is the resolutions are different. Yeah, so a lot of things are being done by, you should follow up Gulab's papers. So what they observe is they take spectroscopy of the central region. So sometimes the galaxy is too bright and photometry is not enough, but spectroscopy will cover you from, in the far UV, will cover from 1300 to 1800 angstrom. So this low resolution spectra doesn't matter. You get many data points for covering the slope, and it's flux calibrated. So many data are there. It's all public. Many of them are public. I think most of it because UVIT has observed less objects in the last 1 year or so. So many data is public, and they're all co-observed. So you should say you don't have any time. I mean, they are simultaneous observation. So you'll get X-ray data and UV data simultaneously. Yeah, you can take a look at many of them. A lot of them are there. Now, many people are using multiple purposes. Now that once the agent is done, you have all the stuff forming things around it. People are doing stuff formation. UV. Yes, here it is important because LAX-PC will be there, S60 is there, and UVIT simultaneous. Yeah, yeah. I don't understand AGN, but I know that you need to be simultaneous. Yeah.
Yeah. Any question from students? No? Anyone? Yeah.
So I don't know if I missed very informative talk. Thanks. So I don't know if I missed third or not. You mentioned that blue lurkers are not identified, or
They are
identified.
They are identified, but they are not. So generally, the Kalamanchu diagram, blue stragglers you expect on top of the main sequence.
Yeah.
But you don't see if the star is sitting here. You consider it to be a main sequence. You don't consider it to be anything different than that, right? But we find some of the main sequence stars to be, our detection limit will be less than this. You cannot detect the main sequence, but some of these get detected.
Okay.
Because they have got a companion.
Okay.
So if you find a companion or fast rotating star on the main sequence, if you find a post-mass transfer system, let me put it this way,
Okay.
and the main sequence star is sitting on the here and not here, it's called blue lurker.
Okay. So
detected both in open cluster and globular cluster.
okay. So I know some field stars that have been identified, which are having high alpha elements and which are also found to be young. And
yeah,
so these are also blue lurkers.
So I have addressed one paper which is not part of the talk. Another paper where what are field blue stragglers? Can we identify blue stragglers in the field? Because these are all with respect to the main sequence. You have a reference. That's when you are saying classifying them as blue lurker or blue straggler. Can we look at field? So field blue stragglers are classified as what is it called? They call blue metal poor blue stars.
Okay.
BMP stars.
Okay.
Blue metal poor stars. So you consider this is the metallicity of this cluster. So any star cannot be bluer than this. So if you see a field star, which is metallicity is equivalent to this blue cluster, find out its color. If the color is bluer than this, then it must be a blue straggler. BMP. They're called blue metal poor stars, but if you look at Preston's paper in 2000, early 2000, they've done a lot of work. Okay. And they have done chemistry also. But then they come up with a conundrum that are they blue stragglers or chemically peculiar stars or accreted stars from dwarf galaxies? So we picked up some 25 of them with binarity known and observed with UVIT. And that paper, we find about 17 of them to be detecting white dwarfs. Okay. And many of them are thick disk stars. Okay. Young, thick disk stars.
Yeah. Yes. Okay. Thanks.
Yeah. Any other question? Okay.
But it'll be interesting to combine the chemistry and what we see as a binarity together. We haven't found time to do that. Yeah.
So if not, student, you can always go through these papers and, if there is any question, you can. So we can stop it here.
Thank you. Thank you.
Thank you.